In the previous lecture, we introduced tensor products of Hilbert spaces. So two Hilbert space HA and HB, we tensor product them, and the result is a Hilbert space that has dimension that multiplies. So if the HA has dimension dA, HB has dimension dB, this Hilbert space has the tensor product Hilbert space has dimension dA times dB. And if ket IA symbolically are an orthonormal basis for HA and ket JB are an orthonormal basis for HB, this tensor product is an orthonormal basis. Kets are a basis for the tensor product states. We said similarly, the algebras, operators multiply tensor product. We take the tensor product, and what it is, of course, the size of them gets much larger. 2 by 2 by tensor 2 by 2 becomes 4 by 4. And what you do is that you take A11 and multiply by a whole copy of the second guy. You see it's asymmetric, and put it here, right? So on and so forth. And the action of it on kets is that when you have A tensor B as an operator acting on alpha tensor beta, A acts on alpha, beta acts on B acts on beta, as one expects. Questions about, yeah. Sorry, I cannot hear well. I cannot.
For fermions, is it true that
for fermions?
Yeah, I thought that like it's an anti-symmetric tensor.
Okay, no. This is quantum mechanics. There's a long story associated with fermions. Fermions are also quantum things. So yeah, this is true, no matter what. I'm happy to tell you more about it. Yeah. Whatever I say, about in this course, actually, for sure, you can rest assured that all the axioms and postulates and basics that I discussed, there are absolutely no exceptions to them. Fermions are like unobservables, blah, blah, blah. It's more advanced. But the laws of quantum mechanics are the laws of quantum mechanics. All right, good. So what is a postulate? It's a postulate of composite systems. It says the state space of a composite physical system is a tensor product of the Hilbert space of constituents. And well, you can read it. Any questions about the postulate? It's just the most natural thing you would do, but it has dramatic consequences, as we discussed. It leads to it allows for existence of states, pure states of the bipartite system that could not be written as a pure state of the constituents tensored together, right? And the simplest way to see this was just a counting argument, right? The number of degrees of freedom that represents a ket that has dimensionality dA times dB is a ket with this dimension. How many real variables does it have? So it's a vector with dA times dB components, each of which is a complex number. So each complex number is 2 real parameters. You have to subtract 1 because the ket is normalized, right? It has unit norm. Everything's good? So this is the counting of the number of degrees of freedom in a ket. That is psi AB. What is it for phi A tensor phi B or phi B? It's 2dA minus 1 plus 2dB minus 1. Good? And it should be pretty obvious that very quickly this just takes over. Actually, it always does. Even for a 2 by 2. Good? All right. That was a general argument. By the way, entanglement is a very, very complex phenomenon. At the level of this course, we're only talking about what I'm calling, it's called pure bipartite entanglement states. Is that clear? The words are self-descriptive. These are pure states of the bipartite system. Bipartite, it has 2 constituents. As you allow for more complicated setups, we talk about entanglement for mixed states of the multi-partite system. That setup, instantly you hit like open problems in math. Not only open problems, but problems that mathematicians have given up on, like incredibly hard or intractable. Yeah.
Why are
It's just extreme. Well, I can tell you more about it. There's no. You should ask the opposite question. Why is something easy? All right. So examples of such states are like Bell states. These are 0, 0 plus minus 1, 1 over square root 2, 0, 1 plus minus 1 plus 1, 0 square root 2. These are bipartite states. Can anyone give me an example of a physical setup where the state is produced? It will be important for this discussion. Can you say louder? Oh, that was a preparation, but like physically, do these states? Well, this is a complicated. I mean, you might not know, but in nature, these states pop up all the time. Natural. These states, not like I said that generic entangled states are all over the place, but these are the Bell states are maximally entangled and they appear all the time. Let me give you an example. Actually, this is going to be important later in this lecture. There are, let's say I prepare in the lab an unstable particle. Example would be positronium. It's an unstable particle we could prepare. What matters is that it decays into 2 photons, right? Now you know if the positronium, the atom that decayed into these 2 photons go in opposite directions, right? Why is that actually, you know? Because of conservation of momentum. If it was initially addressed, if this is moving this way, the other one cannot move this way. They should go in opposite directions and equal angular momentum, equal momentum. Photons have spin, right? Polarization. The original thing didn't have spin. So they must have opposite spin. So now let's use the spin degree of freedom of this by 2 photons that created as zeros and 1. If this is up, the other one must be down. So what is that state? Ket 0, 1. But if this is down, this must be up. What's the other state? All the possibilities, there are just 2 possibilities. This or this. And in general, if you make no measurements, it's actually either in this state or in this state. Right? If you don't perform measurements, it's going to be in a superposition. A process prepared this for you. You did not filter it. Right? So they appear naturally all the time. What I just described is the thinking back at the time of Einstein, early 20th century. There is a much more modern perspective on this phenomenon that I'm describing, but that doesn't matter. Good. So these are maximal entangled states. If I put this, so here's another entangled state, 1.001 plus a number that is, this number is 1 minus this square, right? Because of normalization. So imagine I have C1 and C2, 1 over C1 squared plus C2 squared. Actually, even take it to be real variables. All right. Either have chalk or. So here's an entangled state. P is a number between 0 and 1. And here's an entangled state. Square root P, 0, 1 plus square root 1 minus, no, how do I want to do it? Yeah, 1, 0, okay? So this is a normalized state. It's pretty clear that so P goes from 0 to 1, right? If P is 0, this is unentangled. As I increase it, it becomes entangled. half, like this, oh, sorry, the state that I erased. When this is half, that's called the maximal entanglement. We'll describe that, right? But it's clear that by playing with this, I could push it towards pure states versus not, right? So there are more general entangled states. Any questions? All right. So importantly, the very definition of entangled state was that the state as a bipartite system is pure, but if you look at a subsystem of it, the subsystem is not pure. So if the subsystem is not pure, what is it? In general, a mixed density matrix. And to compute it, we introduce an operation of partial trace, right? Partial trace is what you use to obtain the reduced state, right? So here's the global density matrix of the bipartite system. If it were pure, it would be just ket psi AB, bra psi AB. And then you introduce partial trace. Partial trace is literally trace on system B and do nothing to system A. Here's what it is. Is this definition clear? So partial trace, let's say I have 2 qubits and I'm performing partial trace on qubit 2. As an operation, what's the input of the operation? It's a map that sends 4x4 matrices to 2x2 matrices. Good? And this is the action of the map. I defined it for you, literally. Is that clear? I'm going to make a longer pause because it's very important that this clicks. I cannot make a pause. I have to go. So now entanglement, yeah. Absolutely. Absolutely. And that's going to be important for understanding entanglement beyond bipartite. But the short answer is that there's no understanding. It's too complicated. I'm exaggerating a little bit. Tripartite, four-partite is okay-ish. 5 is already, we're lost. Yeah. Yes, we'll do that. Not that to these. There's a reason I called this P, right? You could have complained from, well, or asked why I called. I'm using. So, although my P's and rows are, but like this is a superposition, right? This is a superposition. But I wrote, well, okay, I will get there. Yes, the short answer. I'm not gonna jump around. Okay, yeah. Good. So in quantum mechanics, there are 2 phenomena that are bizarre. Superposition, number 1. That's weird. Entanglement. Entanglement goes beyond superposition. It's the origin of the root of all the weirdness of quantum mechanics. And today we're going to see how entanglement tells us that realism is doomed. We're going to go through that as an experiment, as a physics rigorous statement. All right. So the one important point that I wanted to stress out last time was that entanglement says that in quantum mechanics, we need ensembles or density matrices even without coarse graining. That is why I revised one of the postulates of quantum mechanics to introduce density matrices. It was absolutely essential. So some books that don't do this, especially books that were written like 1970s, they just ignore this fact. Now, these words are for you guys because you're a quantum generation. I think we were the internet generation. You guys are going to be the quantum generation. Entanglement is a resource, is a quantum resource. It's a valuable thing. We talked about how we used it last time to do. You could use it, spend it to do non-classical or bizarre things. You could do classically impossible things. Example we discussed last time was quantum teleportation. You could use it to do quantum cryptography. You could do Shor's factoring algorithm was one of the first algorithms that showed that you could solve math problems with an efficiency that's classically impossible, right? You use entanglement to do things faster. And can you guys guess how factoring is related to cryptography? Yeah, you might not know, but every time you use your laptop, your phone, all the data that is private, you send an email to someone, this is not shared with everybody, it's all encoded based on the idea that factoring large numbers is hard. Now, Shor taught us that, quantum mechanics is not. So if tomorrow some foreign country that we or they dislike come up with a quantum computer that can efficiently factor numbers, we are in trouble. It's actually a longer story. I'm happy to tell you an anecdote about this. There was a multi-billion-dollar effort in the US to switch from we were using a code that was known to be breakable quantum mechanically. So that we switched to something called lattice code, where we do not know quantum mechanics can break it or not. But then there was a paper that claimed it can. It got so much attention anyway. All right. The question is open still. All right. Quantum teleportation is what we discussed last time. What it does is that you could, it's really voodoo. You have a state, right? You do something to it and it pops up over there. But for the other person to know that it popped up over there, you have to call them, because they have to do an operation based on what you observe, right? So no violation of causality. So I want to highlight from now on going forward, every time we're talking about the rest of this lecture and the next lecture, you should keep an important thing in mind: correlation and causation, right? You might have heard this a lot, that correlation does not imply causation, right? But entanglement and Einstein's confusion, in a sense, or mistake, was all related to this. He was not making a silly mistake. It's just very, very subtle to tell apart causation from correlation. We're going to see how John Bell, came up with an absolutely brilliant way of distinguishing the two, right? Is it clear what the context here is? All right. If not, we'll conclude. Any questions about the protocol? It's a very fundamental protocol. It's just the simplest thing that I describe with 2 qubits, about 3 with a qubit, but it generalizes, of course, to whatever you want, if you have enough entanglement in your bank account. All right. There is something called quantum money. You should look it up. MIT tried to actually even patent it. They failed, but the cool thing about it is what I told you last time. It can't be copied. Entanglement cannot. If somebody is entangled to something, no one else is. It can only be stolen. It could never be reproduced or copied. Anyways, it's a very safe form of money. Not the most practical. Maybe for your generation it will be. I don't know. Who knows? All right, good. So I said all this to say that so these protocols that we're talking about are actually being, well, I don't know why I picked Google now again, because they take this for this. But there are quantum devices here that these are actually quantum computers that achieve these tasks. So teleportation is actually very basic compared to what these guys are capable of doing. They definitely they do a lot more. All right. Yeah.
Do you know what those computers are doing? Like
what they're actually doing? What do you mean? Like
what's
the architecture of it? Like
how it's something they're doing.
Yeah, I can tell you more about it. Yeah, so there is a long story. Let me just talk about it for 1 minute, but then after the class, on Thursday, I'm happy to talk about it. There is a question that remains open. The question is, when it comes to algorithms, you prove that there is an algorithm that quantum mechanics can use that outperforms all the known classical algorithms. But that doesn't mean that tomorrow somebody's going to come up with a brilliant classical algorithm that will do as well. So it is a little bit of a tricky thing. There's a term that people coined, quantum supremacy. We don't talk about it because it's not a good word. Now we talk about quantum advantage, right? Anyway, it's a funny story. We're related to that. But we call quantum advantage. Can quantum computers provably outperform classical computers? But for that, we have to know for a particular algorithm, what is the best theoretically algorithm that will ever exist, right? So a lot of this, the reason you asked, there's an essay is that the first device is called the Sycamore device. And their most important, their claim to fame is that they do something called boson sampling that is pretty darn close to quantum advantage. Depending on who you talk to, they would say that they have achieved quantum advantage. They definitely claim that, but all right. But I genuinely, next slide is really included for you guys because I really think that I will get old and this will probably happen. When you look at these photos, you should make the comparison between that and this photo, 1937, right? This is the first form of a universal computer in Princeton, New Jersey. Do you guys know this guy? John von Neumann, the person who wrote the foundations of quantum mechanics. And this is going to be, this is modern, right? 7 years or so later. These transistors have trillion, this chip has trillions, like billions and billions, not trillions, billions and billions of transistors that are visible in that picture. All right, so we are really, these images are really this era. And this is no exaggeration. I'm not trying to make it. That's just how it is. At the end of this lecture, I have a list of just to tell you how quickly experiments are progressing. I gave you a sense of it last time. I'm not an experimental, so I just copied this stuff from Wikipedia, right? But it's shocking how fast things move. All right. So this is actually a review of the last lecture. I'm going to make a pause. Are there any questions? There's a very famous story associated to this. So von Neumann was at the Institute for Advanced Study. And at the time, the director of the institute is someone you know, Robert Oppenheimer. Oppenheimer was trying to recruit von Neumann in the Manhattan Project. And he famously, they did not get along. They lived down the same hallway. They did not get along. He famously wrote to him saying that I'm working on something that's more important and it's going to change the world more than your bomb. That's a nice quote from history. Yeah. All right. That's vision. So today, what we're going to do is, I don't think I'm going to get to quantum entropy. I'm going to talk about two fundamental operations in quantum mechanics. One of them is called Schmidt decomposition. What is the other one called? Oh, purification. They're both, Schmidt decomposition has a very mathy flavor. Purification similarly, but purification is a deep, it's a very, very useful way to think about quantum mechanics. Well, so they're related. And then finally, at the end, I'll end this lecture by talking about Bell's theorem. We'll talk about EPR, Einstein's confusion, or paradox, seeming paradox, and how he was proven wrong. That's a good physicist. He was proven wrong twice, and both of them are the two biggest accomplishments. One of them is one of the biggest accomplishments we've had in our modern theoretical physics. What's the other place? You guys know? Cosmological constant. Yeah. All right. So what is Schmidt decomposition? Here's a theorem. Schmidt decomposition is a It's basically a theorem. It says, suppose psi AB, ket AB, is a pure state of composite system AB. There exists orthonormal states ket IA of system A. This is an orthonormal basis. Let me actually even call it basis. No. There's a reason I said states. So there are orthonormal states IA and orthonormal states IB for system B, such that the ket could always be written as a sum over I, lambda I, IA, IB, with non-negative lambda i's. Not only they are real, but also they are, because I put a equal here, I could use a basis anyway, and they add up to 1. So you can see that I already used it here, right? These coefficients are called Schmidt coefficients. What does it tell you? It tells you that a generic entangled state, no matter how complicated, when you write it, remember, like when I say, here's a question. This state is obviously entangled, but how about this state? I don't know, like alpha 1 plus alpha 2, 0, 1 plus, I don't know, like gamma 1, 0. It's hard to know. But the point is, no matter how complicated this stuff is, it always admits a form like this. Yeah.
That side is it's at the same psi AB.
Yeah. For any psi AB, you could do this. That's the point. For any pure state of the composite system, you could write it this way. This, at least the first time I saw it, it was mind-blowing to me, but it's actually super straightforward. It's a very, very useful trick. So we're going to prove it. This one slide is pretty simple. Psi is a state of a bipartite system. In general, it takes this form. Let's just make sure everybody follows this part. This should be familiar, right? Where AJKs are just complex numbers, right? Good. All right. So here's where I have to rely on your knowledge of mathematics, linear algebra. There is something called singular value decomposition. If you don't know what it is, I absolutely recommend you look it up, because it's not about this course, it's about the rest of your career. It's all over the place. It says the following. It says that if you have a matrix, you can always, well, let's say if you have a matrix, you can always write it in the following decomposition. A unitary operator U, a diagonal matrix with non-negative elements D, and another unitary V. Have you guys seen this statement? It's very useful beyond quantum mechanics. It's extremely useful. It's no exaggeration to say a huge part of like science and technologies, modern science and technology uses this. So what does it say? Let me repeat again. You take an arbitrary matrix. Doesn't have to be even square. Arbitrary matrix. You could always write it as a unitary U multiplied by a diagonal matrix, with diagonal means only on the diagonal unless you have something. And those coefficients on the diagonal are all non-negative, finally multiplied by another unitary. This can always be done to any matrix. It's called singular value decomposition. Okay, so that tells you that this is a matrix. Let's do a singular value decomposition. You could write it as, so this is matrix multiplication, right? I've written A as U, D, V. D, these are matrices. I know that my notation might not be very obvious, but these are matrices. These are matrices, right? So you get UJI, DII, because D is diagonal, VIK. All right, is everybody with me on the first line? The index I is multiplication of the matrices inside the decomposition, right? It's all good? All right. Now, all that's left to do for you to prove the theorem is to just rearrange these. You take dii out, you write the sum of ujij, sum of kvik. You call these kets ib, and you call these kets ia. dii are your non-negative Schmidt values, or what does that call them? Coefficients, Schmidt coefficients. There you go, you proved it. Now, how do you make sure that the set of ket IAs are orthonormal? Well, it's a one-liner. Take the inner product of them and use the fact that U is a unitary. It's just a rotation. Similarly for IBs. Can you see already what is going on? Maybe it's like too quick, but there is something profound here. Well, it will take some experience. So, yeah. All right, any questions about the derivation? But if you don't know singular value decomposition, yeah, absolutely, it's the matrix trick. All good? All right. Okay, so now what we just said is given an arbitrary pure state, psi AB, let's calculate its reduced density matrix in the Schmidt notation, right? Using the Schmidt decomposition. All right, so what is it? Psi AB is this. What you need to do is you first have to take the ket bra of psi AB to get the density matrix of AB and perform partial trace on B. Is it helpful if I write on the board, or is that clear enough? Okay. So it's pretty straightforward. Sum over I. So this is one ket. You write it here. Sum over I lambda I A I B. And then the dagger of that will be sum over I lambda J. Why not lambda J star? They are positive and real, yeah. And then JJ. So now you know how to do the trace of B over this. I don't know why. It just take the B elements and flips them. So you end up with sum over IJ, lambda I, lambda J, IA, JA, IB, JB. But this is an orthonormal basis, so it's just a Kronecker delta. So you end up with this form. What did Schmidt decomposition do? It diagonalized your reduced density matrix. That's what it did. The Schmidt coefficients are the coefficients that control entanglement, bipartite pure state entanglement. The theory of bipartite pure state entanglement is all labeled by these Schmidt coefficients. That's actually a rigorous statement. Could be turned into a rigorous statement. All right. Let me pause here because I think these are you should try to ask questions if something is unclear. They're innocent looking equations, but they're pretty, yeah.
Those MIs that related to probabilities. One of the states of the composite.
Literally, just instead of your question is a statement, which is correct. Just say it. So this is the reduced density matrix. Ket I's are orthogonal. So what this says is you have a density matrix that is with probability lambda I squared in the state IA.
This is sort of like rate of probability and like nested functions like x, y, and two variables. You know, like it's sort of like a marginal.
I'm so glad you say that. You said that one. It is the margin. I just was not trying to say. It's that. So I don't know if this makes much sense to you guys, but there's probability theory, and if you have a there, I think I made this analogy. Classical states of bipartite systems would be probability measures over two random variables that are independent. How do you get the reduced state of one of them? Conditional expectation. You integrate over the other one, right? That's called marginal. That's a term from probability theory. In physics, depending on who you talk to, we also call these marginals. Quantum mechanics, I might have said this, is a non-commutative probability theory. End of the story. It's a probability theory where your random variables do not commute. In standard probability theory, if you have variable x, variable y, these are random variables, this is equal to y and x. The order doesn't matter. If you just say you're a mathematician, as von Neumann was, and then he said, oh, I'm just going to assume the order matters, you discover quantum mechanics. You don't need anything else. This is the elegance of quantum mechanics. A lot of times, the lesson from 20th century physics is that, in a sense, physics is, well, yeah.
Can you explain part of line 2 to line 3?
This part?
Yeah.
To this. So this part I've just copied, right? This bit I've copied. What have I done? I've simplified this to this. So what is that? Let's write it down. Trace of B, I, A, I, B, J, A, J, B, right? Trace of B, there's a label B here, which says it does not act on A guys. So the A guys come out. Right? So now what you're left with is multiply by trace of B, I of B, J of B. Right? What is that? That just is, whoops, I, B, J, B.
Yeah, maybe. Yeah.
Oh, I'm so sorry. Thank you so much. That's why you should ask questions, because I have typos all over the place. IJ, thank you. Maybe that's why I should do it on the board. Thank you. If there is a typo that you see, say it, because it might confuse other people. Thank you. All right, good. So what did we do? We said we had a pure state, entangled state. Actually, even if the state is not entangled, what is this Schmidt decomposition? What are the Schmidt coefficients of an unentangled state? I have an unentangled state. I can always write it in the Schmidt form. What are the Schmidt coefficients? You know, give me an example of an unentangled state. Yeah. So your I is running over 0 and 1. So your term is ket 0a, ket 0b. That's it. So the sum over I has only one term, which means that 1 lambda I is 1, the rest of them are 0. That's always the case. For pure state, The Schmidt coefficients are, one of them is 1, the rest are 0. That's it. As you expect from here, right? Because this reduced state must be pure. The only way for that to hold is that you only have one of these terms, right? Compute the purity of this. Can you guess the purity? Sum over I lambda I to have. But anyway, it's just a one-liner. All right. So what did we do? We said we had a pure state of a bipartite system. Then, like me and Bob, Alice had a pure bipartite system, and then we described using a reduced density matrix their state in a diagonal basis. That's what we did. Now let's say Alice doesn't know about me. Alice is just given a state. Like us, we are in this room. We're going to describe the state of this room, and it's not going to be pure because it's connected to the rest of the universe. So generically, it's going to be a density matrix, right? You could always diagonalize it, write it this way. You could always assume what's called purification, that this diagonalization came from somewhere in the rest of the universe, somebody holds the rest of this entanglement states. Let's do them mathematically, and then you'll see. They purify you. Your state is not pure. Once you include their state, together you have a pure state, right? This is the reverse process. We started with a pure composite system. The reduced state was mixed, right? Now you're given an arbitrary mixed state, and you imagine somewhere in the universe is the purification of your state. It's a thought, meaning that, well, actually, it has a physical consequence, but given any density, here's a math statement. Given any density matrix rho A, it's possible to introduce another system R, we call reference, and find a pure state psi of AR such that the reduced state of rho A is your state of interest, what you were given. The state psi AR is called a purification. The proof is by construction. Trivial, right? So let me say what I do. I have a density matrix of this room. I first diagonalize it. It looks like this, right? Then I'm going to imagine another system called the reference of R and a pure state of AR that takes this form. Why did I assume this state? Because if you reduce it down to A, you get the state that I have. Then I say R is purifying my state. This is highly non-unique, but it could always be done. Let's pause and think about this, right? It might seem arbitrary, but this actually is physically important and relevant, and it has some consequences. But for now, we're going through the linear algebra. Let's just first nail the concept, what we're talking about. Is that clear? Let me try to give you a description of it. Let's say I'm an experimentalist, so I'm so not. I have a qubit. It's mixed, right? Why is it mixed? Because it's interacting with the rest of the universe, right? The state of the whole universe and my qubit is pure, right? Purification is the statement that let's go rearrange the rest of the universe to find the qubit that is entangled with my qubit. That's always possible. There's always a possible to rearrange the whole universe by unitary. By rearranging means just unitary, right? So that you find what is purified. This is also related to the question that was asked before. monogamy of entanglement. If something is entangled to me, and we are maximally entangled, it's not entangled with anyone else. So in entanglement, it's fair to say if Alice and Bob share entanglement state, we draw a line between them. There are no intersections. Yeah.
State between A and R, or is it a state found in the reference system?
It's a state found in the composite system of you, and reference that reduced to A gives you your state. As far as we're concerned, R is imaginary. Right? You could always imagine.
So it's an entangled state.
Yes. Okay. It's, well, okay, sorry. If it need not be entangled.
It's a composite state.
It need not be entangled. Yes. Okay. When it's not entangled, what is that state? Anyone? When it's not entangled, it's just you have a pure state, you imagine some other pure state somewhere else. It's like, that's a triviality, right? The reason we talk about purification is that we have a state that's not pure and we want to make it pure by enlarging your system. You know, I have a qubit. Remember what we talked about last time? We talked about EPR pairs are like this. I know not Bell pairs. There's a qubit, Alice and I, we share a pair of qubits. I know nothing because my reduced state is maximum mixed. She knows nothing, but together we know all that there is to know. You're given a qubit and you look at it, you don't know anything. You say, where in the universe is Alice that if I come next to them, we'll know everything. Statement is that there exists always an Alice in the universe by a rearrangement of maybe there's Alice and Charlie, half of Charlie and half of Alice. If you combine them, there's one person that has the purification of your state. But there always exists. Yeah. Oh. That's my next slide. This is unitary. R. Oh, sorry. Yeah, that's my next slide. It's on the next slide. It's highly non-unitary because if you apply identity tensor unitary rotation, right, there's still purification. What does that mean actually in the example of me and Alice? So a unitary rotation, let's say we're sharing qubits, and unitary rotation is like rotation. If she has the purification on my system, and she decides to what she used to call X in this direction, this is Y direction, and now she switches them, she still holds the purification of my state. Yeah.
Is this purification state R as well? I mean,
Yes. That's a very good question. Very, very good question. So I'm just gonna leave this for you guys. Now, never mind. Think about all sorts of examples because we don't have time for me to elaborate on subtleties. Okay, good. Everybody's with me. This is a natural stopping point to ask questions because the rest of it is Bell's theorem, and Bell's theorem is even more profound. Well, these are all pretty deep statements, but Bell's theorem is like mind-boggling. It's very weird. So the way I'm just gonna run the story through like a little bit historically, so that you might, because of the terminology you might hear, so that you would be able to recognize. You don't need the terminology, but people use them so that you know what we're talking about. Okay, here's what we were talking about. Okay, let me just, it might sound philosophy, it might sound like pure nonsense hogwash, but what it is, I'm just describing to you. Let's first ask the question, which sounds absurd. Then we're gonna do a test, experimental test, and see that the absurd comes true. What is it? We talked about superpositions. We talked about the statement that before you perform a measurement, there is no way for you to know what the state is. And this is not you being a crappy experimentalist. This is just the way nature is. It doesn't matter who you are. Nobody will ever know. what the state is, right? This gave the fathers of quantum mechanics the impression that it might give you. It sounds like the measurement decides the outcomes. When you measure spin and it comes up, it sounds like the up was decided at the moment by the measurement, right? That's what we're talking about. This is contrasted with what we call realism, which is the system has a spin in a particular direction, has a property. When you observe it, if you're a really good experimentalist, all it does, it reveals to its value. It always had that value, right? In realism, the value of it, that what you read off, is just information that you learn. In the other picture, is created at that moment, right? This is what we're contrasting. Turns out that the realism is absolutely wrong, and we could test this in experiments, and we do that all the time, right? So this is what the issue is. Everyone's with me? We're gonna make it, there are two levels of sophistication we're gonna add. First is Einstein's objection. So Einstein had an objection. And to show his objection, he formulated it. Well, actually, let me just go over this quote because it's kind of nice. Well, you can read it. There was somebody was going for a walk with Einstein, and then he was just obsessed with the fact that when you look at the moon, if you were not looking at it, the moon wasn't there. When the moment you looked at it, the moon just popped up. Or what does it mean for it to exist, right? This is about existence, reality, realism. That's what we're talking about. The system having some property, and when you observe it, the goal of measurement is ideally is that it reveals something to you. But here we're saying that there is no way. It doesn't have a predetermined value, right? So we're gonna, shockingly, this is something we could test in experiments, and we can. We have. All right, let's first run through Einstein's confusion or paradox objection. This, in 1935, and even today, the first time you see it, sounds like a sound argument. It did not convince the physics community for good reasons. And it turned out that they were right. So here's how it works. Einstein, he invented special relativity. He discovered special relativity. So, of course, uses thought experiment. He said the following. Said, let's say Alice and Bob share an entangled state. And this state is 0, 0 plus 1, 1 over square root. And we're going to make them go really, really far away. Now, only one of them is going to perform a measurement. Alice is going to measure her qubit. The moment she measures 0 in this state, Bob's state must be 0. Right? Is that clear? Because it collapses 0, 0. There's no other state in there. If she sees it to be 1, Bob's state must be 1. So now here's a very sharp contrast. If at that moment that Alice performed the measurement, her measurement decided her bit, it should also decide Bob's bit. But Bob is so far away that there is no way on earth the measurement can send a signal. Let's say the measurement device was in charge of like conspiring against you. Like the moment that you measure it is 0, it has to tell everybody around the world that this is what I saw, just show something consistent. But there is no way that they could send a signal because you could arrange for these setups. Alice does a measurement, Bob does a measurement, and they're so far, they do measurements so fast that there's no way for a light signal to transfer, and they come and compare their results, right? So what Einstein said was that the fact that there's no way for a signal to be sent, and the fact that special relativity is true, it means that he concluded, Einstein, Podolsky, and Rosen, these three guys, they concluded that there is, even though quantum mechanics tells you that the measurement is deciding it, quantum mechanics must be incomplete. There must be some future theory that one day we'll stumble upon that will tell us what exactly goes on, because there's no way on earth. He concluded that this seeming non-local, like acausal behavior, it's just because for some reason the quantum mechanics is incomplete. We didn't have an alternative. He just said, this is not the whole story. Turns out that he was wrong. All right, is the EPR paradox or whatever thought experiment clear? Podolsky and Rosen. Yeah. Actually, I should look this up. Rosen, there's a Rosen in physics. I wonder if it's the same guy. Notice in 1935 is when von Neumann published his book, Mathematical Foundation of Quantum Mechanics. This is a really exciting time. These were exciting times. And today is also very exciting times for other reasons. All right, good. Now, people, when this argument was presented, people thought this is philosophy. There was even literally the school of thought that shut up and calculate. The idea was that, okay, quantum mechanics describes what we see. Why does it matter that we argue over what realism is or locality is? This does the job, right? Let's do that. Then there was this guy at Bell Labs. No. Yeah, was he? No, he was at Cornell. I don't know. John Bell. He famously said, I'm an engineer, physics engineer. He did plasma physics, but he said, on weekends, I think about I have principles. That's what he said. On weekend, I have principles. So he spent his weekends thinking about these problems. And surprisingly, he came up with a way of, so what is called Bell's inequality. Bell's inequality is an experiment he proposed, not assuming quantum mechanics. Okay, I'm going to describe it. It does not assume quantum mechanics. It's an experiment. If you believe in realism, if you use realism, you get an inequality. Something has to be less than 2. We're going to prove it in a second. If you use quantum mechanics, it says it could be as large as 2 square root 2. So if you went out there and did the experiment and you found any value larger than 2, realism is dead. That's what happened. The fact that you could design such an experiment is mind-blowing, shocking. But it's so simple. What's funnier is that it's so simple, I can just say it in like 7 minutes. Right? So is it clear? It does not use quantum mechanics. It's just an experiment, right? That he designed that if we're going to see in a second, just the idea that measurements reveal information, they have predetermined value, tells you that some inequality, sum of a bunch of observations should be less than 2. But quantum mechanics allows it to be larger. So if you saw it to be larger, if you found it to be larger in an experiment, that's the last day of realism. You should discard it, right? Forever. Good. So I'm going to describe the measurement. So the idea is that classical reality, but let me just use a little bit more sharper term. It's called local realism. I'm going to say why. Local means relativity, causality, or causal reality. Is confronted with quantum mechanics. This was the genius of the guy, right? He came up with an experiment where there's clash between them. So here's the experiment. Alice is all the way out there, really, really far away. And Bob is in this room. Charlie is sending them particles. And they're measuring spins. Charlie might send them entangled states or might send them whatever states, right? And all they're doing is that they're performing measurements. There are 2 types of measurements they can do. Let's say it's actually literally that. Alice decides so they get a spin, degree of freedom, silver atoms. They can decide they have a measurement device that measures sigma z, the z direction, z component of it. And there's a measurement device that sees X component. Okay? Those are the 2 experiments. I'm going to call them Q and R. That's the convention. I apologize. Because you don't want to say sigma z because that implies quantum mechanics. This is just 2 different types of measurements they can do. Similarly, Bob, when they get their particle, they can do 2 different types of experiments, S or T. The point is that the results of these experiments are binary, either +1 or -1. It's a vector, right? Is it up or down? So let's just pause here because so the proof of it is one liner. let's just see if everybody's on board with the idea, right? So actually, there's one more thing to say. When Alice or Bob, they receive their particle, they don't know a priori which measurement they're gonna do. They're gonna flip a coin, and based on if it's heads, they're gonna do an experiment. One of them, say Bob does S. If it's tails, they're gonna do T. Signals. Good? That's the setup. That's the whole setup. Any questions? Is it clear what the setup is? It's very important because to this day, after the first time I saw this was perhaps 19 years ago, I still get perplexed. Such a thing is possible. All right. Okay. Here it comes. Let me do it on the board. So what are these? Okay, so here's Alice. She can do Q or what was my notation? Q or R. And here's Bob. She could do S or T. The outcomes of the outcomes of these are plus minus one numbers, right? These are numbers, plus one minus one. Good. So I can always calculate this. So I take Q minus R. What is the value of that? What's the value of Q minus R? It's either 2 or 0. If this is 2, Q plus R is 0. If this is 0, this is 2. So one of the two is 0. I'm using real thing, by the way, already. One of them is 0. Good? So pretty straightforward. Then I'm going to multiply this by S. How do you do it? Oh, I'm going to multiply this by S. I'm going to multiply this by T. Right? One of the terms is going to vanish. Right? The other term, this is 2. Or sorry, minus. It could be minus. Right? It could be plus minus. So this result, this is plus 1 or minus 1. The sum is plus minus 2. Those are the only options that exist. Good? I'm just multiplying integers and adding, right? We're going to see that it could be 2 square root. Yeah. Oh, they're not related. So if this is, so just draw a chart. There are 2 options for this, 2 options for this. There are 4 options for this expression and 4 options for that expression. Whenever this is non-zero, the other one must be 0. One of the two is 0. Because they are either, if they are both plus 1 or both minus 1, this is 0. When they are opposite, this would not be 0, but then this would be 0.
Okay, plus or minus. Okay.
They're either the same or not the same. If they are, either way, one of the terms vanishes. Good? Yeah. Yes. I'll get it. So far, I'm saying 2 different things, and I'm going to relate. So, but if the results of the measurement, whatever they measure, this equality should hold. Good? All right. So now let's say what classical reality predicts. Classical reality says in the experiment we just designed, when they flip coins, the value, whether Q is plus or minus 1, I'm going to call this variable little q, this variable little r, this variable little s, this variable little t. I mean, I could use the larger capital letters as well, but that's usually conventional. So classical realism says when before they do their measurement, one of these configurations, you draw a chart, one of them exists. So you could, when they flip coins, there's a probability associated to some outcome. For example, there's a probability for plus 1, minus 1, plus 1, plus 1. Right? This being Q, this being R, this being S, this being T. Right? There's a probability associated to all of these. Okay, so let's do an expectation value of this expression. Good. There are two options. Each term is either 2 or minus 2 multiplied by probability. So if so this is, I have it on the board. This expression is less than 2. Everybody agrees with that? So I can turn my sum into an inequality by just multiplying this by 2. The sum is just probabilities. They add up. This has to be less than equal to 2. It's just saying that if the variables must be 2 or minus 2, as you measure them many, many times, there's no way for, let's say 10 times, there's no way that the sum up to larger than 20 because you have some negatives. Worst case scenario, you get exactly 20, right? Good. This is called the CH-SH inequality. I'm going to get their names wrong. 4 people. Important people, but I'm not going to say it anymore. I'll shut up at that point. All right, good. CH-SH inequality. All right. Good. Now here's an exercise for you. Take your state. Let's say Charlie sends them this EPR pair, this Bell state, and Q is measuring Z component of the spin. X is, this is for Alice. Alice, the 2 choices she has is either measure Z or X. And Bob is either measure Z plus X or Z minus X. These are orthogonal measurements. All right? So just do the calculation. You know how to calculate expectation value of these observables. You add them up in this state, you get 2 square root 2, which is larger than 2. All right? Here's an opportunity to prove realism wrong or quantum mechanics incomplete. Good? I think it takes some staring at these equations, but first you have to do that calculation. It's once you start calculating the first term, you see how it works. It's pretty obvious. Yeah.
Why these are all specifically chosen?
Yeah, because what you want is to find a clash. You wanna find a setup where quantum mechanics and realism have different outcomes. All I need is just that setup. Of course, I could choose them such that I have no paradox, but that would work, right? But if you're asking this is the unique choice, not at all. The 2 square root 2 is the largest you could do. But anyway, there's a very long history of this. This people have studied. This is 1965, by the way. So exactly 30 years after Einstein, Podolsky, and Rosen. All right, let's ask nature. Do we find 2 square root 2? Or do we find anything larger than 2? Turns out that, well, okay, so what are the assumptions? Realism, QRST exist before you measure them. Locality, that when Alice and Bob do their measurements, they do this really, really quickly. They do it very, very quickly, and they're far enough that they can't send a signal. It's also plausible that relativity is violated, but that's extremely unlikely because relativity is the foundation of modern physics. But if you want to be really like a philosopher, you can question that and say local realism. Local means relativity. So the experiments reveal that quantum mechanics wins, and we do see 2 square root 2. And local realism or realism is dead forever. Yeah.
If you use in a table state, that's not negative result between.
Yeah, you don't go all the way to 2 square root 2. You could arrange it to go a little bit higher, but yeah. Also, the violate. So we said CHSH inequality. That's Bell's inequality. And quantum mechanics sees a violation of it, right? Violation of inequalities of this type due to entanglement get more and more dramatic as you increase the particle numbers. This is related to the fact that entanglement is just everything. When you go to higher dimensions, you go to larger number of particles, everything is entangled with everything. All right? Okay. Yeah.
I was just wondering if it breaks relativity instead of like what consequences.
Well, then we will have a problem because we have to explain all the other independent tests of relativity. But so the reason I say this is that I said local realism because philosophers and scientists, when they come up with this, they are extremely nitpicky about what the assumptions are to make a long list, things that we would not even consider, right? And I'm going to say in the next slide, there's something called loophole free. No matter how much of an annoying person you are, you could prove you're wrong. There's loophole free Bell experiments. People have come up with them. That's exactly my next slide, and thanks for the question. So here's the history of it. 1970, they used positronium decay that creates paraphotons that they're separated really far away to run the Bell experiment. They did it, but they didn't have good quality to rule. They had indications of quantum mechanics being correct, but when people went back and they claimed quantum mechanics was correct, but when people went back and studied them, they didn't have enough resolution to make it conclusive. 1972 is the first real violation of Bell's inequality seen, and 1972 was the day that everyone should have accepted around the world that realism is dead. That was the triumph of quantum mechanics. 1998, my favorite experimental physicist, Anton Zeilinger's group, they proved, they saw the violation of Bell's inequality in an experiment that's under strict Einstein's locality. These are all to close those loopholes that we were talking about, right? Like there were just people who were super nitpicky. There would be always some annoying people who say, what if, blah, 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 right? The first loophole-free Bell test is 2015. That's already pretty recent. Now, when it gets wacky, now is when it explodes and gets really crazy. 2017, Kaiser and Zeilinger, they did a cosmic Bell test from starlight that has traveled 600 light years to get to us. They did this with that. So there's a source in the Milky Way that were producing photon lights. That was their Charlie. They did the experiment and they saw a violation. So there's entanglement in states that they didn't even prepare, right? Nature prepared. It got even crazier in my mind. In 2018, they did Bell's test using light sources, quasars, that were 7.8 billion light years away. The universe is 13.8 billion years old. So the universe was half the age it has today. And the light photons that they reach us, you could see entanglement in those. It's crazy. But you see, that was 1 year later. This is how fast the science, this technology is improving. It's nuts. The pace of it is crazy. 2023 is the very first loophole-free Bell inequality with superconducting qubits, one of those devices I was describing. So previous experiments, a lot of them are based on like the one that I just went over. Nature was preparing this. But now you prepare qubits and you want to have entanglement and you want to use entanglement to do quantum teleportation. But to make sure that you actually have entanglement, what you could do is once you prepare these qubits in the lab, you could separate them and do a Bell's test to see if they're actually entangled. And they did this with superconducting qubits that we have here at Purdue. And they separated them 30 meters apart, and then they tested it. And shortly, they saw a violation. Here, at this point, we're not even testing Bell's inequality. We're using the test to see that we have prepared entangled qubits. Right? This is tabletop experiments. Things are getting pretty insane. All right, so this is the end of this lecture. Sorry we went over time. In summary, we talked about Bell's experiment, how realism is dead. Any questions? Yeah.
realism versus quantum mechanics.
Yeah.
It seems more to me you're testing classical probabilities versus quantum probabilities because your quantum state, you're already assuming it's localized in this area too, which means you're assuming quantum mechanics and everything we're observing is quantum mechanics. So
No. Let's just put quantum mechanics aside. Put quantum mechanics aside. What we see is we have paraparticles. Alice and Bob can do two measurements. Forget about, imagine you have never heard of quantum mechanics, right? All that you believe in is probability theory. And the fact that before you do a measurement, this was either +1 or -1. That's all you assume. When we prove this inequality, all that we assume is probability theory and the fact that they had predetermined values. That's all. Forget about quantum mechanics. Now, quantum mechanics says, oh, if I'm correct, I allow for larger values. You say, I don't buy it. I don't care about your linear algebra crap, right? I don't buy it. Let's do an experiment. And then, but you have to play with their rules. They say, oh, there are spinners that come, you do these measurements. You say, okay, sure, I don't care. They have predetermined values. You do the experiment and you're proven wrong. All right. I'm happy to tell you more about it if you have questions, but I have to run because I have another meeting. Thank you so much, guys. We'll continue the conversation on Thursday.